Okay, hi everyone. I'm Christian, a second year PhD at UCLA. Today I'm going to present our work, Gerenuk. This is a joint work between my colleagues at UCLA, UCI, and UChicago. So big data systems are written in managed languages such as Java or Scala. These managed languages and managed runtimes have overhead, and this is a well-known problem. Previous approaches tend to focus on one aspect of managed runtime or object overhead. For example, Skyway focused on improving serialization and deserialization in big data systems. This is the process of taking input bytes and transforming them into objects and vice versa. Skyway improved this by removing serialization and deserialization and transferring objects as is to remote heaps. They found a 1.4x speedup, but incurred a 77% network traffic overhead. Another approach is Yak, which modified GC to better fit data processing lifetimes. They saw a 1.7x speedup, but saw an increased memory usage. Instead, can we find an approach that fundamentally removes all of these object overheads? One existing approach is Tungsten, which is a Spark project. In this work, instead of processing objects, they instead process native bytes, thereby removing serialization and deserialization costs from transferring between native bytes and objects. And because there are no other objects in the system, or less objects in the system, there is much less cost for GC. One downside of the current Tungsten approach is that it's not very general. You can't use all data types, and instead have to use a certain set of simpler data types. In addition, Tungsten doesn't work well with all algorithms. For example, in iterative algorithms, we found Tungsten to be slower than baseline Spark. So in this work, we seek to answer the question, can we find a scalable and general solution to remove all of this object overhead? Our solution is Gerenuk, which contains a compiler and a runtime. We speculatively transformed the user's source code to remove all of these sources of object overhead. We ran across Spark and Hadoop and saw on average an improvement of 1.6x in runtime and a reduction in memory usage by 26%. Notice here that we won in both space and time, and we didn't make trade-offs that the first two approaches I mentioned did. So first, let's step back for a minute and think about what a data processing application might do. Here, this is a worker node which receives input from other worker tasks in the form of native bytes. These bytes are then deserialized into objects. The data is then processed as objects, and the objects are passed through some function, such as map or reduce. Then the output objects are serialized back into native bytes and sent to the next workers. So instead, can we just process the native bytes instead of serializing them into objects? This transformation is called byte inlining. What is byte inlining? Take this object foo with a string field and an int field. To represent foo, we need a header, which contains meta-class information, a reference to a string object, and the integer I. To represent the string, we also need another object, which has its own header and the actual data that it represents. Notice that I doesn't have a header because it is not an object, it is a primitive. Byte inlining is the process of removing these headers, removing these references, and taking both of the payloads and inlining them in some buffer. In this way, we save memory overhead, since we don't need to keep these references and headers. We also don't need to deal with serialization. There's no transferring between these two representations. We just process the native bytes. So what does this transformation look like? Take, for example, this same foo object. If we inline it, and it had these values for the two fields, after the inlining, we would have just the payloads of the string and the integer. Take, for example, this field read, foo.s. We would replace this call, or this read, with a call to a read native function, where we read at a certain position in the buffer a certain length. So here, string comes first in the buffer, so it is at offset 0, and in this case has length 7. So if we read the bytes 0 to 7, we have the bytes for the string. Write is similar, but the backwards process. So if we want to write to the integer field, we know that it's directly after the string. So we go to position 7 in the buffer, and we write the value 10, which has size 4 because it's an integer. So is this a general transformation? No, we rely on two properties of objects. One is confinement. So say that our transformation only is going to transform the foo object. And foo references a string, and bar, which is outside of our transformation scope, also refers to the same string. You can see a code snippet here of how that would look. In this way, foo.s escapes foo through bar. Why is this a problem? If we don't transform all of the code, then part of the code expects objects and part of it expects bytes, and we could break semantics. For the rest of the talk and in our work, if we find such a case that breaks confinement or the second property, I'll refer to this as a violation. The second property we need is reference immutability. So take, for example, this inline string in int. We can write to the primitive field, but not to the reference field. Why is this? If we try to write a longer string into the string position, which is at the start of the buffer, we would write starting at 0 and then to a further index than we originally had. This would thrash data in the buffer, so we can't allow it. We can allow primitive type writes because they all have fixed size. So if we wanted to write to the integer field, then we wouldn't overwrite any further data. So recall that Gerenuk contains both a compiler and a runtime. This byte inlining transformation I've described so far is all done in our compiler. We also have a runtime which enables recovery that we call aborts. I'll describe why we need these aborts later, but first let me describe what they do. So say we start a task, and a task here is a data processing task, such as in Spark or Hadoop. We first start the Gerenuk task, which is byte inlined that we've done our transformation on, and in one case it might just succeed, and that's the end of the story. In the other case, we hit one of those aborts, and we kill the current Gerenuk task, and we restart it. We restart the original untransformed task with the same input that we gave the Gerenuk task. In this way, we can maintain correctness if we get our transformation wrong. And by design of these big data systems, if a task fails, we can restart it with the same input and expect to get the same output. This is because tasks are usually independent and do not modify some global state. So to find these violations, we use static analysis. And when we find them, our compiler will insert abort instructions. Note that an abort is not a system call abort. This is just what we call our recovery mechanism. Two main challenges with this static analysis approach are scalability. Because we are targeting big data systems, this is on the order of hundreds of thousands of lines of code. Additionally, static analysis tends to be very conservative, so we must deal with false positives as well. So to handle scalability, we made the insight that most of the objects created at runtime are data objects, or objects that are created in data processing. In our experiments, we found that 95% of these objects are created during data processing time. We can find data processing by locating the deserialization, which could be the start, and the serialization points, which could be the end. If the user annotates these 2 points, we can limit our scope just to the code between them and just transform data processing. We can do this because data processing is a much smaller part of the overall code, but most of the objects are created here. In this way, we can get most of the benefit of byte inlining while still making our transformation tractable. So even within the smaller section of code, we still need to deal with the two properties, reference immutability and confinement. First, let's think about what a traditional static analysis would do. Say that before the start of the if, there are no violations. During the if condition, there are no violations. This is just a field read. And in the if body, there is a violation of reference immutability. After the body, what can we say? One path had no violations, and the other path had a violation. Traditionally, we must be conservative and say that there might be a violation after the branch. Afterwards, we would just have to stop the transformation because we require both of these properties. So recall our abort instructions that we add with our compiler when we find a violation. By doing this, we can see that now one path will have no violations, and the other path will not continue. If we hit an abort instruction, execution will be halted, and the original task will be started. Because of this, we can think about it as if the aborts are pruning paths that have violations. Why should we do this approach? This is because we find that aborts should be rare in practice. There is a lot of overhead associated with killing a task and restarting it, but we find that most objects in the data processing section are reference immutable and confined. So these abort cases should not happen often. We ran Gerenuk across two frameworks, Spark and Hadoop. In Spark, we ran 5 applications, which were a mix of graph algorithms and machine learning tasks. In Hadoop, we had 7 applications, which were map reduced jobs we found in Stack Overflow. We ran these experiments over the listed data sets and on our 11-node cluster, with the configuration listed here. We found that overall, we improved both memory and runtime in Spark and Hadoop. In Spark, we improved runtime performance by 2x and reduced memory usage by 18%. In Hadoop, we improved performance by 1.4x and reduced memory usage by 31%. Here is a subset of our Spark applications. Here I'm showing our worst, best, and median applications. You can see in our best case, we improve runtime by 3.4x. But across the board, we also reduce memory usage. Memory usage is reduced because we remove object headers and references. And our speed up is because we remove all of these object overheads, such as garbage collection or serialization. We found similar results in our Hadoop experiments, where in our best case, we find 2.1x improvement in runtime. And again, across the board, we reduced memory usage. In Hadoop, we saw slightly lower improvement because their data types tended to be simpler, so didn't have many object references and didn't find as much improvement. So what about violations? As I mentioned, violations should be very expensive, but in practice, over our real applications that we found, the abort instructions were never hit. So to still quantify how expensive aborts are, we simulated aborts in PageRank. And you can see that as the number of aborts grows, this becomes very expensive, and we slow down applications. We also found one application that did some Stack Overflow analytics that had a violation, and we see a slowdown there as well. So in summary, I present Gerenuk, which contains a compiler that speculatively transforms a program to use byte inlining. It also contains a runtime that handles assumption violations. We ran Gerenuk across 2 frameworks, Spark and Hadoop, and found both performance increases and reduction in memory usage. And with that, I conclude, and I can take questions.
Hi, so I'm Chinmay from Utah. I had a question with respect to your byte inlining. So suppose my struct had, a cache padded member. Suppose I have an integer that I chose to cache align, for example. Are you going to preserve that alignment and that padding once you inline it into your buffer, or because it seems that this could create like networking overhead. For example, if I'm trying to send that out the network, now I'm also going to send those padded bytes out when I might not want to.
Yes, we might copy those bytes, but overall the memory saving should, or the memory overhead should be low if we did that.
What about the network overhead? Suppose I were to send that out the network, I would also be sending those padded bytes too. So did you evaluate that, or is that future work?
I believe our network overhead should be close to baseline.
Okay, thank you.
So I found it very impressive, the degree to which you went to synthesize these aborts and measure the worst case, and it does seem like you're in a really nice sweet spot that no one really needs to do this. But this is also early days, relatively speaking, for graph processing. And I guess what I'm wondering is, going forward, if we did have things that made the kind of updates that cause these aborts, are there ways that programmers could write their code that made it easier and more efficient for you to handle these cases? Or do you think the right way to go is to maintain this level of transparency?
So previous approaches dealt with this by forcing manual code refactoring. We took this approach because for the most part, there aren't aborts and we can just automatically transform the program. But yes, there is a trade-off between that automatic transformation and manual refactoring.
Do you have a sense of like where the crossover point is in that trade-off?
I think that's an interesting question. I'm not exactly sure where that would come.
Okay, that's fair.
Yeah.
All right.